GPT-5.1 can solve a meaningful share of state bench tasks once. The problem is doing it reliably. This is fluid coding and AI, and today, the memory question is not whether an agent remembers your name. It is whether memory helps an agent complete stateful work the same way 5 runs in a row. The experiment has 3 conditions: no persistent memory, simple vector memory, and structured procedural memory. The useful question is not, can the agent retrieve an old fact? The useful question is, does memory change task completion and consistency on the same benchmark subset with the same model, the same protocol, and the same number of repeated runs? If memory cannot move those numbers, it is probably just extra context with better branding. StateBench is Microsoft's open-source benchmark for stateful task agent evaluation. It covers travel, customer support, and shopping assistant tasks. That matters because the agent is not just answering trivia. It is working inside a sandbox with bookings, orders, accounts, carts, policies, tools, and mutable state. A task can require checking eligibility, calculating a fee, getting consent, and then changing the environment. That is much closer to operational agent work than a memory demo about personal preferences. Microsoft's launch post gives the cleanest published no-memory baseline. GPT-5.1 without memory averages pass at 1 scores of 0.48 in customer support, 0.52 in shopping, and 0.56 in travel. Those numbers say the model can often complete the task once. But the reliability metric, pass to the 5th, is much lower: 0.26 for customer support, 0.38 for shopping, and 0.30 for travel. That gap is the story. Pass at 1 is optimism. Pass to the 5th is operations. If an agent succeeds once and fails the next 4 attempts, the demo can still look impressive. The product cannot. StateBench makes that visible by asking whether the agent succeeds across repeated runs of the same task. Travel has the best average pass at 1 in the published baseline, but only 0.30 pass to the 5th. Sometimes capable is not the same thing as dependable. The no-memory condition is the control. It still gets the current task, the domain tools, the conversation history, and the model's general reasoning. What it does not get is a reusable memory pulled from past trained trajectories. This baseline answers the first engineering question: how much does the model already solve without a memory system, and where does it fail from skipped steps, missing confirmations, or wrong tool order? The vector memory condition is the simple memory baseline. Take trained trajectories or extracted learnings, embed them, and at test time retrieve a few similar notes through the benchmark's read-only memory tool. This can help when the new task resembles an old trace. It can remind the agent about a policy pattern, a common correction, or a useful sequence. But it can also retrieve the wrong lesson. Similar text is not the same as the right procedure. The structured memory condition tests a different idea. Instead of retrieving loose chunks, it retrieves procedures, required checks, forbidden shortcuts, tool order, consent points, and common failure patterns. That lines up with how long graph and long chain describe long-term memory. Semantic memory stores facts. Episodic memory stores experiences. Procedural memory stores how to do things. For StateBench, procedural memory is the interesting bet because the benchmark is full of tasks where order and preconditions decide success. Take a travel task. The agent may need to find the booking, check cancellation policy, calculate penalties, offer alternatives, get confirmation, and only then mutate the booking. Vector memory might surface a similar cancellation conversation. Procedural memory should surface the checklist that prevents the skipped confirmation or the premature tool call. The same pattern appears in customer support and shopping. The value of memory is not nostalgia. It is fewer policy misses, fewer invalid state changes, and more consistent execution. A real win is not the agent-used memory. A real win is higher pass to the 5th on the same subset, with pass at 1 holding steady or improving, user experience not regressing, and cost staying acceptable. A false win is easier. Better recall, more verbose answers, or a higher average score with the same consistency problem. For agent memory, the metric has to be task reliability. Otherwise, the system may feel smarter while still failing the work. There are important caveats. ST8T bench is new. The official GitHub leaderboard was still marked as coming soon at research time, and no local benchmark artifacts were available in this workspace. The Microsoft numbers are first-party published evidence, not a reproduced run here. The benchmark is also synthetic, and some procedural and informational scoring uses an LLM judge. So the right claim is narrow. State bench is a useful controlled testbed for memory, not final proof that one memory design wins everywhere. The practical verdict is simple. Run the boring baselines first. Start with no memory. Add vector memory as the cheap retrieval baseline. Then test procedural memory to see whether distilled workflows improve consistency. Judge the result by pass to the fifth, pass at 1, user experience and cost on the same state bench subset. If procedural memory wins there, it has earned more attention. If it does not, the memory system is probably adding complexity without operational value. That is the useful bar for agent memory: better task success, better consistency, and fewer stateful mistakes. If this helped clarify how to test memory instead of just demo it, like the video and subscribe to Fluid Coding and AI.